Before we take a look at how we implement heaps, let's take a look at how we use them. So in this short main program, I have two linked heaps, one with integers and one with student records. And I also have a binary search tree with integers, and we'll add the same elements to that tree as we do the heap. And that'll let us see what the difference is when we print those two data structures out. So for the student records, I have several different records I'm adding. Those students have a name and a GPA, and the ordering constraint on that record would be the student's name as a string. And since the string starts with their first name, we'll put them in alphabetical order of the first name. So we're going to print we're going to print all three data structures, the two heaps and the tree. And then we're going to remove the minimum element first from the student record heap, then from the number heap. So let's run that and see what happens. And you can see that the tree and the heap, even though they have the same elements, they're in quite a different order. And then here's the heap displayed. And of course, there's a lot of output there because it's printing out all those records. Then as we remove the elements from the students, we get the students in the order of their first name. So Adam, Andy, Carrie, and Daisy come out as the first three elements. And then for the numbers, we get 1, 5, 8, and 15, which would be the smallest elements in this particular heap. Our heap interface is going to extend the binary tree interface we did earlier, and is going to add several methods. First off, we need a method to add because binary tree doesn't have an add method built in. Remove min, which will take the root element off the heap and then replace it by another node that exists. And then find min, which will check what element the new root node is storing. And our heaps will be made up of heap nodes. That node will extend the binary tree node that we did with the binary tree class. And it adds one new data member, and that is a reference to that node's parent node. This allows us to move up and down the tree. In the binary tree and the binary search tree, we only were able to go to the two children. So if we wanted to find a specific node, we had to start at the root. In a heap, if we're at a child node, we can go back up to the parent using this parent reference. So the rest of the methods are essentially going to do the same thing that we did with the binary tree. We're just going to add this parent reference, and we initialize that to null in the constructor, and we'll set that in the code. We'll have getters and setters for the parent and the element. And we're going to use these heap nodes to build our tree. So we start off, our linked heap class is going to extend the linked binary tree class that we saw earlier, and it's going to implement the heap interface that we saw just now. We're going to add a new data member. So we already have the root from the linked binary tree, but we're going to add a last node reference. We're going to use that reference to determine where the last spot is that we've added a node so that we can determine where additional nodes need to be added or removed. Because remember, with a heap, it's always going to be a complete tree. A complete tree, if you will remember, is full at all the levels until you get to the bottom. And then on the bottom, every node is over to the left. So here's an example heap, and you can see that the heap property is maintained. Each node is smaller than the elements stored in each of its children. And this is a complete tree because it's full in these first two levels, and all of the nodes on the bottom level are as far to the left as possible. So the next node we would add would be a left child of 6, then a right child of 6, left child of 8, right child of 8. Let's see how we implement that data structure. So the constructor is just going to call the binary tree constructor because that'll handle setting up that empty tree. But where we're going to have things be different is going to be with this addElement. And this will also be different than the linked binary search tree as well. So first we create a new node and that's going to be the node that stores our object. If there's no nodes in the tree, the root will be null. We set the root to be the new node that we just added. Then we're going to call this method getNextParentAdd, and that's going to find which parent we're going to use to put the new node under to maintain the complete tree property. Now, once we have this parent, we have to determine, does it have children already? If the left child is null, that means there's no children. So we set that parent's left to be that node. Otherwise, it has a left child but doesn't have a right child, and we know that because the nextParentAdd method returns the node that will be the parent of that node. So we know that there's no right child, so we can add the node as the right child of that parent. We set the node's parent to be whatever was returned from nextParentAdd. And then now, the last node that's stored in our tree is going to be set to the new node we just added, because we're keeping track of where we added the last node. Finally, if we have more than one element in the tree, we're going to call this HeapADT method, and that method is there to make sure we maintain the proper heap ordering. So there's two helper methods that we need to look at for our add method. The first is this getParentAdd. If 7 didn't have a right child, then 9 would be the last node we added, and we're going to get the parent, its parent. And notice 9 is the left child of the node with 7. Now, in this tree, 11 is the last node, so what we need to do is eventually get to where 6 is. So since 7 has 2 children, what I need to do is get to 7's sibling. Now, the way we're going to do that from 11 is we're going to get the parent, we're going to find its parent until the parent is a left node of another node. So here, 11 is the right child, so we get its parent, and now we're at this as our current node, and we're going to say, is this the left node of my parent? And it is. Since it is, we're going to swap over to the right subtree. Now, if this parent doesn't have a right subtree, that means that it's now the parent. But in this case, it has a child. And once we get to this child, we're going to go all the way to the left to add our node. So now we know that in this case, there is no child. So we're going to set this as the new parent node, and we'll add the child there. Now, when we have a child down here and call add again, notice now it's the left child, so it's going to stay there in this first loop, and then it's going to go to the right subtree. There isn't one, so this would still be the parent. Where this gets complicated is, let's suppose we were full all the way here, and we wanted to make 8 the next parent that we add to. So here, we're going to have a node here in that case. We would stay in that first loop 2 times, then we get to the last node, or then we get to this parent node that's a left child. We swap over to the right subtree, and then go all the way to the left, and that would give us that parent. One other case is, let's suppose we don't have 9 and 12 here. Let's suppose 12 was the next node added. As we're moving up to a node that's a left child of its parent, we would get to this point, and now we're at the root. So the root's going to be a special case. If we get to the root in that first loop, then we're going to drop all the way down to the left. So we would just go left, left, left forever. So that's 3 different cases. And hopefully you can kind of see that in this picture as we walk through the code. And you're probably going to want to come back and forth between the code and this description to see how that works together. So going back to the code, here's the loop that gets us to a left subtree, and technically actually a left child. So notice this isn't a left child, but this is. This is a left child, but this is. If we had a right child here, this wouldn't be a left child. This isn't a left child. We would have to go up to here, and so on. Then if it's not the root, we're going to get the parent's right child, and that parent would not have a right child. Otherwise, the last node would be in that right subtree. So that's the parent. Otherwise, If it does have a right child, that means that we have a bigger tree that we're cycling through. So we're going to get that right child, and then we're going to loop until we get to a point in the left subtree where there's no left child. That would give us that node. Now, this is the case for when we get to the root in this first loop. And in that case, we would just go all the way to the left. And once we find a node that doesn't have a left child, we know that would be the new parent. So there's a lot of complicated things going on here. And the best way to really understand what's going here is to try to trace it out yourself with several different examples. The heapify function we use once we've actually added that to the heap. We have the node in the right place, but that node may be storing an element that's smaller. So what we're going to do is we're going to go from that node to the root. And as long as what we're storing in the child is less than what's stored in the parent, then we're going to swap that element and then move to that parent. We're moving that element up through the heap until it gets to the point where the heap property is maintained, where it's smaller than its children and larger than any parents it may have. And notice this would go all the way through until potentially the root.